Okay, so we went through a significant portion of topic 15 in class back when we had to go to school. So I just want to review the basics here, go through a couple of examples for you, and then turn you loose on your homework. Hopefully, with this, you remember to bring your book home, and hopefully, you have a calculator that will do the normal distribution function for you, and occasionally the inverse normal. So again, you saw this chart. The very first thing that you need to do is identify what kind of a variable we're talking about, because that then determines how we proceed, what conditions have to be met using our central limit theorem. Okay, so we'll come back to this. We'll refer back to it. But let's just go through some basic examples here. So for the first one here, it's just indicate whether the question pertains to a sample mean or a sample proportion. Part A, how likely is it that the average height in a random sample of 100 chief executive officers exceeds 69 inches? So if you're the one collecting the data, you go to this chief executive officer, and what kind of data are you going to collect? You're going to ask, or maybe even measure, and find out how tall the person is. They're going to give you, or you're going to collect a number, which means that this is a quantitative variable, which means once you have all of that, you take all of those numbers and you would find a sample mean. Part B, careful. How surprising would it be for more than two-thirds of the CEOs in a random sample of 100 to be taller than 69 inches? So you're going to find out how tall these people are, but then you're going to put them into two categories. Are you taller than this or not? It's a yes or no proposition. That's categorical. You are going to find a sample proportion. C. What's the probability of the random sample of 25 students at your school has a grade point average greater than 3.0? What are you going to collect? What's your GPA? They're going to give you a number. That's quantitative. That's a sample mean once you average all of those together. Part D, what's the probability that a random sample of 25 students at your school produced a sample mean sleep time last night of less than 7 hours? What are you going to ask them? How many hours of sleep did you get last night? You're going to get a number. A number is quantitative. That will produce a sample mean. For part E, what's the probability a random sample of 25 students at your school finds that less than 90% of the students know their mother's birthday? What kind of question are you going to ask? Do you know your mom's birthday? That's a yes or no question. That's a categorical variable. You are going to find the sample proportion. Again, you have to determine this. How we proceed with the central limit theorem depends upon what kind of variable it is. All right, so let's take a look at this one. If you remember back several topics ago, they were talking about candy bar manufacturing. On the package, the advertised weight is 2.13 ounces. It varies according to a normal distribution. The mean, mu, is 2.20 ounces. The standard deviation, sigma, is 0.04 ounces. So for the first part here, what's the probability that an individual candy bar weighs somewhere between 2.18 and 2.2 ounces? So again, we're looking for probability. We're going to need our cumulative normal distribution function. And they've given us the upper bound and the lower bound here. We need two z-scores. So again, for the first one, we're going to take the given, subtract the mean, and divide by standard deviation of the whole thing, 0.04. Well, in our numerator here, isn't that negative 0.02 divided by 0.04? That's negative 1/2. And for z number 2, we'll take the upper end, 2.22, subtract 2.20. Hey, wait a minute. That gives me a positive 0.02, positive 0.5. So now we're looking for the probability where the negative 1/2 is the lower end, positive 1/2 is the upper end. And with your calculators, oh my goodness, let's not do that. So again, for these menu, looking for a probability from a distribution. And we're looking for a cumulative distribution function. And our lower bound there was a negative 1/2. The upper bound was a positive 1/2. So our probability of that happening is 0.3829. Part B, you decide to take a sample of 5 candy bars and calculate the sample mean. Does the central limit theorem apply here with a sample of 5? Wait a minute. 5 is not greater than or equal to 30. However, notice that conjunction there. We're dealing with a quantitative variable, the weight of the candy bar. We've got a population mean. They told us it was mu. They gave us the population standard deviation. They told you that was sigma. We're talking about a quantitative variable here. We can use our central limit theorem if n is greater than 30 or when the population is normal. And what did they tell us? It varies according to a normal distribution. We are then cleared to proceed. Calculate the probability that the sample mean weight falls between 2.18 and 2.2 ounces. Well, okay, the first thing we need to do here is for our sample, we need to know the sample standard deviation, which again, going back to our chart here, we're going to take the population standard deviation, sigma, and divide by square root of n, our sample size. So our S for our new standard deviation, 0.04 divided by square root of 5. So this will give us a sample standard deviation of 0.0179. I'm going to try and be consistent here and go to 4 decimal places. So again, we've got our two values here, the upper end and the lower end. We need to recalculate z-scores. So we'll take the 2.18, subtract the population mean mu, 2.20, but now we're going to divide by our new standard deviation, 0.0179. So that'll give us a z-score of negative 1.1173. And for z2, well, okay, we're going to do the same thing that we did before, 2.22 minus 2.20. Just like before, that's going to give us 0.02, but now we're going to divide by the new sample standard deviation, and this will be positive 1.1173. Nope, F2. So now we're going to put in the negative 1.1173 as the lower, positive 1.1173 as the upper. And the probability of taking a sample of 5 candy bars, weighing them, finding the mean of their weights, the probability that the mean weight from our sample is in that same range. Sorry, the probability here is about 0.7361. Okay, so now again, let's compare the probability of just one of them falling in that range. I mean, that's pretty good. The probability of taking a sample of 5, finding the mean weight of those 5, the probability of that jumped significantly. Jumped. So hopefully I'm emphasizing that so you can get part E right. How do you expect this probability to change if the sample size were 40 instead of 5? Okay, let's figure out if you're right. First thing we need to do here is, once again, recalculate our sample standard deviation. They told us before the population standard deviation 0.04. We're now going to divide by square root of 40. So we're going to use 0.0063. Z1, again, the 2.18 minus 2.20, which will be 0.02, divided by our new sample, larger sample size, standard deviation of 0.0063. Gives us a z-score there. Well, for the lower end, that will be negative. For the upper end, it will be this positive 3.1746. So this one will be negative 0.3 1746. And the probability of taking a sample size of 40 bars, finding the weights of each of those candy bars, and then finding the mean of all of those weights. Point 9985. Did you get part E right? Again, I was trying to lead you in the right direction there. If our sample in part A is just one individual bar, for the next part, when our sample is 5 of them, so the sample size went from 1 to 5, our probability increased. And then from B and C, where the sample size was 5, to now E and F, where the sample size is 40, it increased. Our standard deviation decreased. The positive z-score went up. The probability of it falling between more than 3 standard deviations to the right and the left is pretty much most of the probability that's very nearly 1. Okay, so that's how you would have to proceed if it were a quantitative variable. Can you guess what's coming? The American Veterinary Medicine Association, yes, that's a thing, 2008 said about 2.8% of all households owned pet bird. So we've gotten away from with cats and dogs. So if you took a simple random sample of 2,000 American households, what does the central limit theorem tell you about repeated random sampling? So for your 200 American households that hopefully you found a way to take a simple random sample that's representative of everybody, what are you going to ask them? Do you have a bird? And they're going to respond with 15? Ooh, no, hold on. The question was, do you have a bird? Not how many birds do you have? It's a yes or no question. That is categorical. This is different from the previous example. Now we need to check with our central limit theorem, that very last row going across there. Check with our central limit theorem to make sure that it applies here. Make sure that our sample size here compared to pi, the population proportion, is sufficiently large. Well, it says we are going to try and take a simple random sample, so that's good. But is that sample size enough? So we're going to take, and we're going to say, in this case, that pi, according to the AVMA, is 0.028. So if we're going to take our 2,000 households times the 0.028, that should give us 56. And yay, that's bigger than 10. Trying to be complete with this, we also have to check the complement of that. Do you remember that? N times 1 minus pi. Well, in this case, again, if we're saying that pi is 0.28, the complement for that should be 972. That's a bigger number. We should be fine here. And this turns out to be, yeah, 1944, which is bigger than 10. We can apply our central limit theorem. So now what's it tell us? The shape should be approximately normal. If we do repeated random sampling, we figured out what proportion of those households said that yes, they had a bird, no, they didn't have a bird. Graphed all of those. The shape of all of those should produce an approximately normal curve. It should be centered at approximately 0.028, the value for pi. And then the spread of all of our repeated random samples. Oh, we have to calculate what our sample standard deviation would be by taking this row right here, pi times 1 minus pi divided by n, and then take the square root. So in our case, we'll take the 0.028 times the 0.972 and divide it by our sample size of 2,000. Hopefully you can see an advantage here of, yes, this proportion is much bigger than the value for pi. You're going to have to do the arithmetic eventually. At one point or another, you might as well do it, get it out of the way. So this will then give us a value of about 0.0037. Okay. Now again, if you were going to do the graph, you would take this and multiply it by 3 for 3 standard deviations. That would give you 0.0111. That's not too bad. And then again, combine that with our center. So the 0.028 plus 0.0111, and we would go out on the upper end here to 0.03911 and take 0.028, subtract 0.0111, and the lower end should be at 0.0169. Sorry, let me. Okay, so that's the first part of it here. We take a simple random sample, 2,000. The central limit theorem tells us our sample size is large enough to apply this. And if we do repeated random sampling, the shape will be approximately normal once we graph all of those sample proportions. It should be centered at approximately 0.028. And we can finish the graph there by calculating standard deviation, figure out upper and lower points on our normal curve. Suppose one of your samples gave us a proportion of 2% of the households had a pet bird. Does that result give you evidence that the real proportion of bird owners is not the reported value of 2.8%? Well, let's check with our lovely z-scores. So our sample had a proportion of 0.02. We're going to subtract the reported 0.028, and we're going to divide by that standard deviation that we just calculated was 0.0037. So that should give us a z-score. Now again, this is below the value for pi, the population mean. So we're going to get a negative 1.621 as our z-score. Now, what's the probability that for any random sample here, we're going to come up with 2% or lower? So if we're looking at everything from that negative 1.621 and less, I'm going to leave that lower bound at negative infinity, and we're going to put in negative 1.621 as our upper bound, and this will tell us the area from that all the way on down to the left, and that's a probability of 0.0525. Does that mean it's impossible? No. I mean, we got something that was greater than 0, so it's possible. Does this mean that it's likely to happen by statistical variability? Well, I wouldn't say likely, but it'll happen more than 5% of the time. Okay. Does this result give you evidence that the real proportion of bird owners is not 2.8? No, I don't think it does. Although this outcome is pretty close to, I think we have previously defined a probability of 0.05 as rare. This turned out to be a little bit above that standard. So do we have evidence that the real proportion of bird owners is not 2.8? No, we don't. We don't have a reason to suspect that it is false. Okay, hopefully that all makes sense. From your textbook, starting on page 321, on your Surface so that I can access it remotely. Keep your distance. Try numbers 7, 12, 14, 16, and 17.